Hi guys, how are you? Few things before we start. Completely new topic. The KSC trip. So I'm sorry, but 28 is not working anymore. I don't expect a huge crowd. I mean, it's probably a few people who are coming. Now I sent you a message saying that it's now the 14th, but that may not work for the NASA gentlemen who may be there. So it's still fluid at this point. I don't know. But I understand that the 14th is an exam day for many people. Someone sent me an email. I don't remember the class, but yeah. So 14th for now, we'll see what happens. I want to remind you that the STK certification deadline is the day of the last test, which is April 19th. You have until the end of the day, which is 11:59 p.m., after which I do not accept any more emails or justifications. Please accept these, because if I have deadline, I have deadline. Otherwise, I don't. So try to work on it, because you have 19 days, right? Yes?
So for the CK certification, do we just upload a screenshot of the email on campus, or what?
Whatever email they send you, you forward it to me, you upload it, and I'll see it, because I can see if it's overdue. Canvas shows me when you upload an assignment after the deadline, it becomes pink, it changes color. There's something that should. So please try to do it by the 19th. I have more than a third of the class with level 1 certification. 33 people, I think, and 5 or 6 with this level 2. And that will carry over for Aerospace Design 1, by the way. I've done that in the past. So if you have extra points in this class, you have extra points in the next class as well. Yeah. Okay, so today we are going to start something which is a lot of fun. Spacecraft. Relative motion, which means we have two spacecraft involved. One could be a virtual one, but in principle it's two physical objects that are flying in the vicinities of each other. And we want to represent, with some equations, the dynamics of this relative motion, and hopefully control it. And along the same lines of what we've done with transfers, impulsive maneuvers, we'll find solutions for impulsive trajectories, impulsive maneuvers, to do rendezvous, for example, to drive spacecraft 1 to match in space with spacecraft 2, and other maneuvers of that kind. Why is this important? Well, it's what we do on a regular basis to send stuff to the ISS. To send supplies and fuel to the International Space Station. There's a few other missions that have come up as assembly of smaller units, so that's basically rendezvous down to the point of docking. NASA is looking at Mars missions where they would send people separate from cargo, and then the two spaceships would dock at some point in Martian orbit. So it is absolutely not science fiction. It's something that we have done for a long time at this point. I think the first rendezvous and docking example dates back to the beginning of the space race, really. It was not autonomous, it was with people, but we've done it for a while. So, but before we derive those equations, there's a few concepts we need to refresh and or introduce today. So, the first one is, well, by the way, what does it mean close proximity, or what does it mean to say that they are relatively close to each other? It depends. Usually the equations that we'll derive, hopefully by next time, if not we start today, they are valid when satellites are on top of each other, which is the docking condition, and no more than maybe a couple of kilometers or so away from each other. Which is a lot if you think about distance that you need to walk, but in space your orbits are thousands of kilometers of radius, so they're pretty close. They're pretty close satellites. I think the International Space Station, there are some regulations about getting close to the ISS where I do not remember the radius of the sphere around it, but it's in the order of kilometers if I'm not mistaken. So you don't want anything flying a kilometer from the ISS which is uncontrolled, for example, because it's close. Okay, so the first thing that we need to refresh, which you have seen already because you've done it since we started integrating equations of motion, is state space representation, but I want to do it again and a little more formally, which is, so this is ingredient number 1, which is a way to write in a compact form, in matrix form, a system of differential equations. So I'll start with an example which is actually the equations that we will derive. I'll just give them to you, and eventually we'll derive them. So let's say that I have this system of differential equations, x double dot minus 2 omega y dot minus 3 omega squared x for now equals to 0. And then we have y double dot plus 2 omega x dot equals 0. And finally, z double dot plus omega squared z equals 0. Where omega is a constant, it would actually be the angular velocity of an orbit, but for now it's just a constant. And here you could have inputs. You could actually have non-zero values, but for now we don't have any input. So these are 3 linear second-order differential equations, right? It's 3 of them. You can see that easily. There's no linear expressions in x dot, x double dot, and the same for y and z. There's no cosines or tangents or divide or anything like that. It's all linear expressions. And they're also time invariant. All these coefficients, 2 omega, 3 omega squared, etc., they are constants. They're not changing. So this is a system of linear time invariant differential equations, or LTI. So we don't usually, so what x, y, and z are, it will become clearer later on, but I'll little spoiler here. These are the Cartesian coordinates in the LVLH coordinate system that we have introduced for the Gauss variational equations, local vertical, local horizontal. So these x, y, and z will eventually represent basically, if this is your spacecraft number 1 and this is the associated LVLH coordinate system, they will represent the projections of the vector rho that connects spacecraft 2 to spacecraft 1, okay? So x, y, and z represent projections of that vector in that moving reference frame in that coordinate system. But we'll get there. So we do not like the way it looks. I want to write it in a different form, which is the state space form. And again, you have done this. We have done this together, but we're going to repeat here. I'm going to define the state vector big X, capital X, which is made of 6 components. And these 6 components are, so this is an LTI system, okay? Well, what are my variables here? The independent variables are x, y, and z. What is the highest order of the time derivative that you see there? It's 2. So that 3 times 2 is how many inputs you need in this state vector. And you start populating it with the variables themselves with no time derivative, and then you go to the first time derivative, and you stop there. Basically, you stop at n minus 1, where n in this case will be 2. Is the highest time derivative you see. If you had x triple dot, then you would have to go to x double dot in here. But usually we are dealing with physical systems and equations of motion and Newton's laws, where very rarely, if not never, I would say, you see anything above a second order time derivative, right? Accelerations, angular accelerations, it's all we deal with in equations of motion, and you see 2 dots. Make sense? Okay. Well, okay, with this substitution, I'm not doing anything particularly strange here. I'm just defining a new variable, big X. You go into those equations and you get, what do you get? X double dot will be x4 dot, right? And then you have minus 2 omega, y dot is x5. So I'm basically going to remove x, y, and z, and the time derivative, and I will just have the new variables. So that's x5. What else? Minus 3 omega squared, x is x1 equals 0. That's right. And then I have x5 dot, which is equal, plus 2 omega x dot is x4 again. Yes, equals 0. And finally, z double dot would be an x6 dot plus omega squared z is x3, bless you, is equals to 0. So with this procedure of defining the state vector that contains the variables of your differential equations and their time derivatives up to the n minus 1, where n is the highest order, you substitute this new variable into your original differential equations, and all of a sudden the highest time derivative is 1. It's just a trick to bring everything down to just a dot instead of 2 in this case. So that's the first step. And then the second one is, well, you just move everything that is not a time derivative to the right. Very simple. x4 dot is equal to 2 omega x5 plus 3 omega squared x1. x5 dot is minus 2 omega x4. And x6 dot is minus omega squared x3. Okay. At that point, what I want to really obtain a state space representation of my system of differential equations is being able to write that system in a compact form where I have the big X dot equals a matrix that I'm going to call A that multiplies the vector X itself. This is my state space form of that same system. Tell you why we care about doing this, but let's do it first. Well, how do you do this? You just set the stage and populate the matrix A. So here you have x1 dot, x2 dot, x3 dot, x4 dot, 5 and 6. Okay. What is the dimension of the matrix A? It must be 6 by 6 because it multiplies a 6 by 1 vector here, which is x, and it gives me another 6 by 1 vector. So there's no choice. And now you figure out what goes in here. And of course, my matrix is probably too small to write everything. Well, probably not. So what is x1 dot? I don't see it anywhere in this equation, right? But it's just an artifact of this change of variables. x1 dot is which one? It is x4. 0, 0, 0, 1, 0, 0. x1 dot is this multiplying this row multiplying this column. It's x4, right? x1 dot is x dot, which is also x4. And with the same type of reasoning, you move this 1 over 1 position, you get x2 dot, and the same for 3. And that's it for the first 3 rows. Then x4 dot is my first equation there. So I do see an x1. So here I'm going to write 3 omega squared that multiplies x1. Nothing with x2, nothing with x3, nothing with x4, and a 2 omega x5 and a 0 there. I'm sorry the numbers are so close to each other, but that's a matrix with 6 components. x5 dot, x5 dot. It's only 1, right? Fourth position, 0, 0, 0, and I have a minus 2 omega here, and then 2 other zeros. Everybody following? The last one also is only 1 component I care about, so in the position x3, so I have 0, 0, minus omega squared, and then 3 zeros here. And that's your matrix A. Okay, so I have basically manipulated that system so that it looks like x dot equals AX, where now x is a vector and A is a matrix. Why do you do this for LTI? Because there is a lot of theory for linear systems that you have seen probably in many other classes, where these matrices are used to establish properties of the system. If it's stable, if you basically, for example, start from any generic initial condition for position, x, y, z, and velocity x dot, y dot, z dot, and you let it go, will it go to 0 by itself? Will it converge to 6 zeros or not? As we'll find out, this particular system of equations does not want to go at 0. Actually, is not stable. If you put two spacecraft close to each other, unless they are exactly on the same orbit, perfectly on the same orbit, and they experience the same exact perturbations, which is extremely difficult because, for example, the drag force could be slightly different because they are different, maybe in shape or size. Unless everything is perfectly ideal and they are exactly the same, in that case they may be flying one behind the other and nothing really changes over time. But in general they tend to diverge from each other. We'll get there. But this is one of the reasons why we want to write systems in this form, because we can analyze the eigenvalues and eigenvectors of this matrix and establish if the system is stable, for example. Right? You've seen these things, right? In other classes. Okay. Now, in general, these zeros may actually not be zeros. They could be inputs here. So they could be a vector u of 3 different channels, ux, uy, uz, which pretty soon for us will become thrusters that I can turn on and off, for example, so that I'm actually providing a forcing component to these equations. And so, associated with this, you could have a matrix B that will look like this in this case: 0, 0, 0, 0, 0, 0, 0, hold on, 1, 0, 0, 0, 1, 0, and 0, 0, 1, that will make you rewrite the system including input. So if my free dynamics with no input was x dot equals ax, now if I do have that additional 3, maybe independent forcing functions, I can add this term, right? And that's why I've chosen B in this form, because I need to map a 3-component column vector into a, I think I skipped one, right? I'm missing one, yes. I need an additional line of zeros. Just make space on top. 1, 2, and 3. So again, my control vector can be ux, uy, uz. I'm just trying to be general. You don't have to have the 3 of them, but you could have all of them. So does it make sense what I'm doing here? If I have 3 inputs available, maybe some are off, or all of them are used, then B will map these inputs back into my equations. And you've probably seen this stuff already in some form. So this is really how you would have a system of linear time invariant differential equations expressed in state space form with input as well. And again, this U could be different, this B will look different if U doesn't have all the 3 components. The most general form that you have probably seen is actually this one. Where this is really your equations of motion. Go back to Dynamics 101. You have a system, systems of particles, a rigid body. You choose certain type of coordinates to represent what's going on. You apply principles, the laws of mechanics to find the equations of motion. This is what you get, okay? In this case, I'm lucky that I get linear equations, for example. This is what allows you to represent what is going on, the physics of the problem. But then, reality is maybe different. This is what you measure. So the Y is usually what we call the measurable output, which may be X. So I'm imagining that C is an identity matrix, and D is 0, well, in that case, you are able to measure the entire state vector. Say that the state vector, like in our case, is position and velocity, right? Maybe you have some kind of sensors that can measure both position and velocity on board your spacecraft, or whatever it is that I'm representing here. For now, I have not connected those equations that I'm using as an example to actual spacecraft motion, but we will. But maybe I'm not able to measure all that. In fact, Satellites can figure out their position, for example, from GPS. If you are below the GPS constellation, you can have a GPS receiver on board, and you can figure out your Cartesian coordinates, but that doesn't measure directly velocity. It's not something for which you have an actual device on board. You have to extrapolate from Kalman filters or other ways of processing data what is your velocity. So what I'm saying is that the C could be, for example, in our case, if x, again, is this state vector, that C could actually look like, let me think about this. Well, if I'm measuring only position, the Y will have to look like basically only X, Y, and Z. Say that this is really the only thing I can measure, okay? This is the only thing I can see, so what do you put in here? Right? Make sense? And actually, that's it. I don't need it this long. Do you see that? So this is how, in math, we represent, again, the equations of motion, and then whatever my sensors can give me, because my sensors may not be able to give me everything that is going on in this vector. I may not be able to measure every component of this state vector. Maybe I'm able to measure x, y, and z. Maybe just x and y. I don't know. And it's up to me to figure out, to estimate what the other ones are, if I am good enough. And then there may be also this component du, where the output can be affected by the input as well. There may be some physical systems where the fact that you're applying control to your system is going to affect the measurement. But for the most part, for what we will do, we will assume that since we're not doing navigation or sensors here or any of that theory, we'll just assume that we can access the entire state space. We can measure position and velocity somehow. That's not our focus, okay? But this is to complete state space representation. This is really the procedure. Start from a system, make all the time derivatives that are not one, that are above one, disappear with this substitution, and rewrite it in a matrix form. And figure out basically what A and B are. So for us, this is not really important for this class, the Y equation. But the first one is. Now what happens if, do you have any questions? By the way, no questions? Everything is clear? You've seen this stuff? What happens if the equations are not linear? Well, the idea is pretty much the same. Somehow you redefine a state vector so that you substitute in your equations and you make all the second and above time derivatives disappear. So in a nonlinear case, you may have equations that basically look like this eventually. x1 dot, after you do your state space substitution, is a function, nonlinear function that I call f1 of x1 all the way to xn, if my state vector is of dimension n. Then I may have controls, inputs, and say that that has dimension m. And this could also be a dependence. There could be a dependence on time in general. And then you continue down to xn dot, which is possibly a different function, nonlinear function, fn, of the same variables, okay? So with the nonlinear case, you simply have, after you substitute your state vector so that the second time derivatives disappear, instead of having those nice equations that are all linear, you may have nonlinear combinations. But the bottom line is that you bring all the first time derivatives to the left, and you rewrite these in compact form as x dot equals a big F, or just a general F, of x, u, and t, where x has the same meaning as before, is my state vector. This big F is collecting all the linear functions. It's just a way to represent that I may have different linear functions here for each single variable. This is my control inputs, and this is time. So nothing really changes except you can't use, in principle, linear theory if you have something that is nonlinear. We don't like nonlinear things, usually. So what do? I'll give you an example after we cover the theory. For nonlinear systems, which I'm actually not going to cover, I'm going to do something else. What if I have a nonlinear system and I do not care necessarily about its overall behavior? I care about what it does in the vicinity of a reference condition. What do? Approximate, which is called linearization, right? You linearize. Guys, you're engineers, you do this all the time. We do this all the time. In fact, this is what we're going to do for our 2 spacecraft. So say that this is our planet, okay, some continent here, and say that we have our first satellite, and I'm going to start calling this the chief satellite, and say that its position is called RC with respect to the center of the planet, and I have, and here attached to it, I define the X, Y, Z local vertical, local horizontal coordinate system. This is supposed to be a 3D representation, so Z is not pointing at us necessarily. Just to be clear, this is what I called, what the book calls for the Gauss variational equations, RSW, okay? I just call them X, Y, Z, but that's what they are. And so my other satellite now is located up here. I call this the deputy, okay? And this is what I called before the raw vector. And of course he has its own position vector RD with respect to the Earth. So what if the deputy doesn't go too far away from the chief? So in this case, the chief's condition that will collapse to a circular orbit to find those equations is my point of linearization. What if I try to linearize what this guy does with respect to the chief, as long as it doesn't go too far away? I should get some linear equations for the motion of the deputy, right? What you guys have done so far is that in the simplest of the models, you've done this. You have integrated these nonlinear differential equations, right? That's the very first thing that we have done at the beginning of the semester. Put that in MATLAB form and integrate these nonlinear equations. And these are obviously nonlinear, right? In RD. There is an RD cubed. There is a denominator. So that's nonlinear enough. But what if I know that deputy is not going away from another satellite, which I call the chief? What if I care about representing its relative trajectory with respect to the chief? Maybe I can try to linearize this equation and project it into this basis x, y, and z, and have an easier representation for what that raw vector is doing over time, which is exactly those equations I gave you before. Okay? So when we have a nonlinear system, we usually tend to linearize if we have a reason for that, if we have a point with respect to which we want to, that we don't want to leave, we don't want to go too far away from that point. So in this case, you would linearize about a condition that we can call x0, u0, for example. That point of linearization. So let's do this formally. Maybe here. Okay. So what my point of linearization, or state of linearization, let's call it that way. Let's call that some condition x0, u0 that I care about. Okay. Well, I can write any particular state x as x0 plus some delta x, There's nothing wrong with doing that, of course. And then u, I can always write it as u0 plus delta u. Right? There's nothing wrong with doing that. So what I want to obtain, I want to somehow represent, well, not necessarily the delta u, this is really what I care about, to represent how this is changing if I remain relatively close, and that depends on how nonlinear your system is, as you know from Taylor expansions, and you've done this in the past. It depends on how much your system is nonlinear. A linearization could be very good going away from the point of linearization if your function is not extremely nonlinear, but it may last only for very close approximations if the function is very nonlinear. So what do I want is this. I want to find a system of equations that look like this for delta x. Delta x dot equals some a0 delta x plus some b0 delta u. So I want to approximate what this is doing in the vicinity of this reference point here, okay? This is my state of linearization. And I want to obtain a linear time invariant system. And the reason why I'm calling these A0 and B0 is because these two matrices will depend on the point I choose for linearization. How do you do that? Any ideas? Ideas? How do you linearize a function? If I give you this, this is a nonlinear function, scalar. It's not a vector, okay? It's nothing as complicated as having multiple nonlinear functions, it's just one. And my point of linearization is 0. Okay. What is a linearized version of this function? No ideas? Series expansion, does this sound familiar? So this is my f of x, right? I'll call it that way. Is f of x plus in 0 plus df dx computed at x0 that multiplies x minus x0. And this is your first order approximation. So if you just stop there, this is approximating f of x in the vicinity of x0, right? Memories that sound familiar? A little bit? No? So in this case, what is it with that particular x0? What is the cosine of 0? 1. What is this? The derivative is minus sine, right? Minus sine of x that you need to compute at x0, at x equals 0 basically. It multiplies x minus x0. This is 0. Don't we say that the cosine is approximated by 1 when the angle is small? Is that right? You want to do that with sine. What is the linearization of the sine function? How do you approximate the sine function when the angle is close to 0? It doesn't go too far away from 0. Do you remember that? It's x, right? So let's prove that. X is almost equal to, what is the sine of 0? This is 0. And then the derivative of this is the cosine of x computed as 0 that multiplies x minus x0. So bottom line, this is cosine at 0, which is 1. I get x, because x0 is 0 as well. So you do that in a bigger scale when you have a system of equations, but it's pretty much the same thing. So this is what you get. You get an x big big X, the entire state space vector. X dot is equal to x0 dot plus the delta x dot, which is equal to, of course, f in x0 plus delta x, u0 plus delta u, and time, which is, now I do start the series expansion here, and I have f that has to be computed at the point of linearization. Keep in mind that this f, for me, is the collection of all the nonlinear functions that I may have. So if I have a system of n differential equations, I may have n nonlinear functions that are just compacted in this form here, plus df with respect to x computed at the point of linearization times delta x. This is the equivalent of that x minus x0 right there, right? Plus, what is this df with respect to x or df with respect to u? These are all vectors. This is a vector, this is a vector. What are these things? Delta u plus terms that are of superior order or order, second order in dx and du. So if I neglect these because I am linearizing, then this equal becomes an almost equal, right? That's what you do when you linearize. You just stop at some point at the first, the linear terms in delta x and delta u, and you ignore the rest. So what are these things here? What is this? This has a name. What does it mean to do the partial of a function which is a vector of functions with respect to a vector of variables? What is the name of that? Never seen Jacobians before? Never heard of the expression Jacobian? Yeah? You should have, right? So for example, this one is going to look like this. It's the partial of the first function f1 with respect to x1, and then you keep going with the same function all the way to xn, and then you go to the other ones. So in the end you have the last one, which is dfn with respect to x1 and dfn with respect to xn. And this matrix, after you do all these partials here, then you substitute whatever is your linearization point. So if your x0 is just a bunch of zeros, everywhere you see x1, x2, x3, etc., you substitute 0. And so this will result into a matrix, which is the one I'm calling A0. It is a matrix of numbers. Because I take the partials, then I substitute specific values for the x's, and I get a matrix. And this matrix is of dimension what? If my, I don't need this for now. So if my x is of dimension n, and my u is of dimension m, for example, right? I have n components for big X and m components for u. What is this? It's n by n, right? Remember, that's what I want to obtain. I want to obtain something like this. Don't be thrown away by the fact that I put the deltas in front of this. This is exactly like writing what I had before. X dot is equals to ax plus bu. But I'm using the deltas just to underline that I am moving away from a specific reference state. It is a little change with respect to x0. It's not actually x. It is a delta x. Now, if x0 happens to be a bunch of zeros, then you can call it x. But that's just a more general way. So that's a0. Likewise, your df, these are the matrix, df, du, computed in 0 will look like this. You have df1 with respect to u1, first component of the u vector, all the way to df1 with respect to um. I said that I have m of them. And I go all the way down to dfn with respect to u1. And here I have dfn with respect to um. So you take these partials, whatever they look like, you substitute x0 and u0 wherever you see them, and you get another matrix, which is your b0. And this has dimension n by m, as it should be. And that explains why I call them A0 and B0, because the moment I change the point of linearization, those numbers you have to substitute are going to change. I have an example. Well, we've done it here, right? I've done exactly what I'm writing there in a general form. I've just done it for a single function, right? The procedure is exactly the same. It's just that you have to do it for more functions. What time do we have? So I have this example for you. Then next time we'll definitely start doing it for spacecraft routing motion. But I needed to make sure we are on the same page. So minus 5x1 minus 4x2 cubed. This is enough to tell you this is a nonlinear system, right? x2 dot is equals to x1. x3 dot is equals to 3x1 minus 3x3 minus 8 tangent of x4 plus sine of a single input, u. I only have one input here. x4 dot is equals to x3. So this is already expressed in a way that makes it easy to see the state space representation. It's already in state space form, right? So this piece here is basically your F1. This one here is your F2, right? This is your F3. And this is your F4. You see that? Okay, and the linearization point is x0. I have 0, 2.5, 0, pi over 3. I say it's transposed because that's how we have organized the vectors in column vectors. And u0 is only one variable, is 0. So this is my linearization point right here. Or state, rather. Okay. So I just need to take all those partials in there. So df with respect to big X. And then we'll substitute the numbers. Okay. Who wants to start? What goes in the first element here? 1, 1. That's F1. First variable is x1. That's a minus 5, right? Then I'm still on the first row here. So x2 is the second one. I have minus 12x2, right? Partial of f1 with respect to x2. Make sense? If it doesn't, tell me.
Should
Yes.
x2 be squared?
Yes. Thank you. This is F4. The next is x3. I only see a 5. Now, how big is my state vector? It's 4 components, right? In fact, in my point of linearization is 4 values, so I still have another element here. What is the last one? Right? It's the partial of F1 with respect to x4. What is that? 0. Okay. Second one, it's pretty easy. This is F2. F2 is simply x1. What is the partial with respect to x1? Is 1, 0, 0, 0. The last one, I'm sorry, not the last one, third one. F3, partial with respect to x1, it's 3. x2, nothing, it doesn't appear. x3 is a minus 3. This, I'm sure we all remember that this is what it is, 1 over cosine squared of x4. That's it. I don't do anything with u. This is the matrix A. I don't take partials with respect to u here. And the last one is 0, 0, 1, 0. Now, you have to substitute these numbers wherever you see x1, x2, and x3, and x4. So, if I want to compute these in the point of linearization, well, just plug in the numbers. Minus 5 is not going to change. X2 is this 2.5. So if you square these and you multiply these times 12, I have a minus 75. Okay? 5 is not going to change. 0, 1, 0, 0, 0, 3, 0, minus 3. I have 32 for this one. You can double check at home. This should be right. 0, 0, 1, 0. End of the story. This is your matrix A. Make sense? And then if you want to compute B, you do the same with B. Now, this is a little simpler, right? What is df with respect to big U? Computed in 0 is, what is it? What is the partial of that? First of all, what is the dimension of this? You have one input, 4 states. It's a 4 by 1, right? Just a column. Because I just need a column that multiplies a scalar to map back into a column of 4s, or four variables, right? So, okay. So partial. So I have partial of f1 here with respect to the only variable I see, which is u, which is appearing in the third equation. So the first two don't have anything. 0, 0. Here I have a cosine of u and 0, which has to be computed at the point of linearization. And the only variable I see here is u. What is the u at linearization? Is 0. So this is simply 0, 0, 1, 0. And this is your B matrix. Yes?
Why is this B not B naught?
Yeah, it's B naught, yeah. Good point.
The same thing applies to A?
Yep, yep, absolutely. If I change this point, I'm going to change the numbers that go in here. Up to this point, until I substitute the numbers, this is all fine. The moment I change, I introduce the point of linearization in the actual variables, then you are depending on where you are in terms of linearization. If you change that point, the numbers will change. Okay, we have a few more minutes. I'm going to start what we want to do, which is applying all this to that deputy satellite, which for now is, all we know is that it's going to move probably close to the chief, and then we'll make some assumptions to derive those equations that I gave you at the very beginning. So, if you go back to that sketch that I've erased, this is the relationship you have among those three vectors. Okay? Right? Should watch the time. Yeah, 2 minutes. I'm going to stop in a second. So, if you use, remember, this is the chief vector, position vector. Remember the definition of LVLH, the x-axis is aligned with RC. The z-axis is aligned with the angular momentum of the orbit, and then you cross the two and you get the y, right? So this is supposed to be a 3D view, okay? But if I do that, and I project all these vectors into this basis, I get RC plus x in the I direction, or x hat direction, it's the same, plus yj plus zk. Does it make sense? This is me expressing the deputy's position vector with respect to the center of the planet in LVLH. I'm just projecting it in that basis. RC is aligned, this is the center of the planet, is aligned with x by definition. Now, what do I need to do at this point? I said that I want to linearize this. And this is exactly what we're going to do. So, no perturbations. We're going to stick with Keplerian dynamics. But I still want to linearize this. So I need to start taking derivatives of this vector here. First one is RD dot, which is equal to transport theorem. RD, time derivative of RD with respect to LVLH, plus the angular velocity of LVLH with respect to ECI, which is my inertial reference frame, crossing RD itself. Is square root. Where is the square root? Oh, no. It's just I was separating. No. That's a box, yeah. I don't know. Separating stuff. I'm going to stop here. I'm going to tell you to start doing this by yourself. Try to start thinking about what is this. It's not that difficult. What is the angular velocity of the local vertical, local horizontal coordinate system with respect to ECI? What is it? What is this? Using this representation for RD, and then we'll have to do a second time derivative and then figure out how to linearize at some point. But you can start taking these time derivatives as a good exercise. Have a good weekend.
Do you need us to do anything